Now we're going to start on Unit 7. This is matrices. We will explore row echelon form, matrix row operations, determinants, solving systems, matrix inverses, and matrix applications. The first unit is about row echelon form, all right? So 7.1. Let's investigate how to form a matrix, put it in row echelon form, and then apply it to systems of equations. So a matrix has a dimension given by m by n. It's like saying 3 feet by 4 feet, or 10 inches by 12 inches, where m is the number of rows, n is the number of columns. Each entry in a matrix is given by a, I, comma, j, where a is located in the ith row and the jth column. So that's just a way to have a location for each entry in the matrix. All right, so here comes a general matrix that has m by n dimensions. So this is an m by n matrix where the very first entry in the top left-hand corner is going to be A, 1, 1. This is going to be the jth column. The columns go vertically, and then the ith row is going to be located on the left-hand side. All right, so the rows go horizontally. Now, where would A, 1, 2 be located? Well, that's going to be just to the right of the very first entry, because it's going to be in the first row, second column. And then we continue on until we get to the end, which is going to be A, 1, n, because n should be the last column of the matrix. And then when we go down, the entry below A, 1, 1 would be A, 2, 1. That's in the second row, first column. And that's going to go all the way down to A, m, 1. We can also go diagonally to the end, and the very last entry on the bottom right-hand side is going to be A, m, n. So just notice that, for example, that entry right there, I is going to be equal to 2, j is going to be equal to 1. Second row, first column. So example number 1. Determine the dimensions of each matrix. I'll also give you a few entries that we can pick out. So the first matrix in the top left corner, A, this is going to be 3 rows and 2 columns. That's a 3 by 2 matrix, where the A, 2, 1 entry, well, that's going to be the second row, first column, and that's 2. Part B, 3, 4, 8. That looks like a vector, which we studied in a previous lesson. So this particular matrix is 1 row and 3 columns, 1 by 3. A, 1, 3 is going to be -8. The next one, C, that's going to have 2 rows and 3 columns, a 2 by 3 matrix, where the first row, second column entry will be -2. And then the last one is a 3 by 3 square matrix. equal rows equal columns. And then we have the third row, second column. That entry is going to be y. Matrix operations that we can perform without changing the characteristics of a matrix. We can switch any rows. So for example, see this one down in the corner, 3x negative y 0, x, y 5. I can switch those rows and I could write x, y 5 and 3x negative y 0. That matrix would have the same characteristics as the original. I can also multiply any row by a scalar quantity. And then I can add a multiple of a row to another. So take a look down at the bottom. If I multiply the first row of this matrix by 2, I'm going to distribute that to everything, and I end up with 6x, negative 2y, and 0. Then I could take the first row times 1 and add it with row 2. So R1 plus R2. And I would end up with 7x, negative y, and 5. If you think about it for a second, this is almost like solving a system of equations. Because if I were to combine two equations, I would do 6x plus x and then get 7x. And I would add negative 2 with y, and I would get negative y. And then 0 plus 5 equals 5. So all of that is the same operation as solving a system, which you've already done in the past. Given a system of equations, we can write what's called an augmented, AUG, augmented matrix, by using only the coefficients of the system. Let's let the first equation, 3x plus 4y equals 2, be the first row. And then I'll let the second equation be the second row, just coefficients. Add my brackets, and there you have it. That is an augmented matrix with 2 rows and 3 columns. Most teachers and in other places you see a line there that allows you to tell where the equal sign is. So basically, this is the x column, this is the column of y's, and that's what it equals. Let's do it. Solve the system. 3x plus 4y equals 2, and 2x plus 5y equals negative 1. How can we use row operations to make this thing simpler? Well, what if I multiplied the first row by 2? And I multiplied the second row by negative 3. That would give me another matrix with entries 6, 8, 4, negative 6, negative 15, 3. You can put your extra line there to differentiate the equals side, but you don't have to. It looks a little bit better, but I can see now if I put 6 and negative 6 together, then I'd get a 0 somehow. So why don't I take R1 plus R2? That will give me a matrix. Leave the first row alone, but the second row will be 0, negative 7, 7. It's getting there. How about if I multiply the second row by negative 1/7. Now I have zeros and ones. But it could get even more simpler. Let's multiply the first row by 1/6. Now it's looking pretty nice because the diagonal is all ones. And then there are strictly zeros below the diagonal. So see that diagonal there when you have ones and 0 underneath. That is called row echelon form. It becomes pretty easy to solve this system of equations. Because if I look at the bottom row, that tells me 1y equals negative 1, and therefore y equals negative 1. And then if I look at the top row, that tells me x plus 8/6 y equals 4/6. And if I solve that equation, then I get an answer of x equals 12/6, and that's 2. So take a look at what we've done. Try lining up the system of equations and solving it like you would with elimination or substitution. You should get the same answers. What we just did was called Gauss-Jordan elimination. All right, so that's putting a matrix into row echelon form, named after Carl Gauss and Wilhelm Jordan circa mid-19th century. So that's in the 1800s. Carl Gauss on the left, Wilhelm Jordan on the right. He's got a nice beard. Gauss, Jordan. Elimination is the same as solving a system, except that the matrix must be composed of zeros and ones. That is going to be called reduced row echelon form. Example: 1, 1, 1, 0, 0, 0, 0, 0, 0. 3, 4, 5. That's an example of a matrix, an augmented matrix in reduced row echelon form. So zeros on the top of the diagonal and zeros on the bottom. Solve the system of equations using Gauss-Jordan elimination. I encourage you to pause the video and try and come up with an augmented matrix using row operations that will have ones along the diagonal, a 0 on below it, and a 0 on top of it. All right, in this example, it would be a smaller matrix. All right, here we go. Augmented matrix. Let's multiply the second row by 3. Keep the top one the same. I'm only changing the second. Then If I take R1 plus R2, I should get a 0 there. So R1 plus R2. Again, I'm leaving the top one the same. But on the bottom, I'll have 0, negative 10, 10. It's getting there. Let's multiply the second row by negative 1 over 10. Halfway there. All right, now what can I do to this top row? Maybe I can multiply by negative 1/3. I'll have 1, negative 2/3, 11/3, 0, 1, negative 1. This particular matrix right here is in row echelon form. The diagonal is 1s, and there's a 0 underneath it. But we want reduced row echelon form. So now, let's try and put two row operations together in one. I'm going to take the second row times 2/3 and then add it with R1, the first row. My result. Now I'm leaving the second row the same, but the first one will be 1, 0, and 3. This is a perfect reduced row echelon form matrix. And remember that this first column represents x, and this second column represents y. So that means x is equal to 3, y is equal to negative 1. And we're finished. Have a nice day.